I would also like to thank the organizers, the local organizers, for providing such an engaging social program and good facilities, and the scientific committee for allowing me to speak. Also, I'm impressed by this headset, as was Richard, although I don't feel like I'm about to fly a helicopter. I feel like I'm about to bust a move like Michael Jackson. But I won't. So. Maybe later. Okay, here's an outline of the talk. I told you some of these things before at previous CTs, and I'll call your attention to those facts as they come up. But for now, the outline is I'm going to tell you a little bit about a certain way of describing Martin-Löf type theory in a maybe more categorical or algebraic form. And it involves some applications of the theory of polynomial functors, which I found surprising when I noticed them. So there's a kind of nice connection there between polynomial functors and some operations in Martin-Löf type theory. And then I will remind you about homotopical models of Martin-Löf type theory, which I told you about before, and how to strictify them into this more algebraic form. And then I will move toward an axiomatization of these models that I have in mind. And this is, of course, part of the homotopy type theory program that Andre mentioned yesterday, and it's maybe the subtitle is Toward an Elementary Infinity Topos, something like that. So, okay, so Martin-Löf type theory, I'm sure you've all seen it at some talk or another, and you don't want to go through all the details of it because it's quite an elaborate, arcane machine. It has all kinds of ingredients, everything from types and their terms to these exotic type-forming operations, although, of course, intuitively, these are families of types and elements of the families, and then sums and products of such a family of types. There are these contexts of variables, which already came up in a talk recently, I don't remember which one, but the idea is that you have a kind of iterated dependency of variables, and then another type which may depend on this variable x, and then that one can have a variable, and so on. And so these give rise to a category consisting of these lists of dependent types and their variables, and then substitutions between them which are given by terms that are substituted for the variables. I think I'll just leave that to your imagination, how that works. But, okay, and just a little bit more detail here about these contexts. I said there's the kind of iterated dependency, and you can build new contexts out of dependent types, which are dependent on previous contexts of variables. There are the rules of inference. This is, of course, a kind of logical system, like a deductive system for constructing objects and proofs about the objects. It's patterned on natural deduction. I didn't invent this. This is, Per Martin-Löf and constructive type theory and functional programming languages and so on. So it's a well-established, outside of category theory, well-established system of foundations of mathematics, which has a constructive character, and of course it's a appealing target for categorical logicians to analyze and give semantics for. So these are the contexts, these are the sums, the kind of rules for the dependent sum operation. Here are the rules for the product. I'm not going to go through them, but they're, well-behaved type-forming operations. And then here are the substitutions that I mentioned before between the contexts, and the substitutions act on the types and on the terms in this kind of way. If I have a substitution from this context to that, think of that as a term, and then you can plug it into this term, and you can plug it into that type, and you get a new term in that context. So that should look pretty familiar to you. That's a kind of pullbacky operation or a composition operation. Okay, so one model of this system, which I won't go through in detail, was given by Seeley in the 80s. Seeley described how to model this thing in locally Cartesian closed categories. And the operations, the sigma and the pi, are the ones you expect in the LCC. They're the left and right adjoints of the pullback, and the pullback is modeling the substitutions. So that was a pretty nice model. It gave us some insight into what this Martin-Duff type theory is talking about. It's talking somehow about the slices of a locally Cartesian closed category and all the base change operations there. However, it wasn't long before the type theorists pointed out that this really is not a proper model of their system, because there are a lot of coherence issues that come up when you start to compose pullbacks, right? You're only pulling back, it's unique up to isomorphism, and the successive pullbacks don't have to actually functorially cohere. And so what you have is a kind of incoherent, or at least not a strict model of the Martin-Duff type theory, whereas the Martin-Duff type theory is a very strict computational gadget which has a good behavior on the terms, and you can compute with these terms, and the model that we have in locally Cartesian closed categories is not really adequate to the logical system that the type theorists are interested in. So they've come up with their own models, some of which are categorical, one of which is called a category with families. And here's a description of something that is equivalent to the category with families model of Martin-Duff type theory. It's not locally Cartesian closed, it's a different approach. And the approach is this: we're going to use what I'm calling a presentable natural transformation. I'm going to call a natural transformation presentable if its fibers are all representable. This is sometimes called a representable natural transformation, which is a little confusing. So I'm changing that terminology a little bit. And in a category of presheaves, it's nice to know that these presentable natural transformations have this equivalent description. They're the ones that are tiny, in the sense that the push-forward functor, the right adjoint to the pullback, itself has a further right adjoint. And that's just because the fibers of this thing are all representable, and if you have an index category with finite limits, the representables are tiny in that sense. So this is a family of tiny objects. So I'm going to use that to give a model of this type theory, and here's how it works. It turns out to be the same thing as this notion of a category with families. So this is kind of the first step in my, if you will, algebraic axiomatization of the Martin-Duff type theory. Is just the basic structure of the dependent families, the dependent terms, and the substitution operations. So I'm going to think of the contexts as my index category. The context and substitutions, that's the index category. And then over that, I have two presheaves, the presheaf of types and the presheaf of terms, and the substitutions act then on these presheaves. That was this operation that I showed you a minute ago. When you substitute into a term, you get a new term in the other context. When you substitute into a type, you get a new type, and that's obviously a presheaf on the contexts. So that's the idea there. And then, so here's a little bit more explicitly, here's the interpretation. A type in context gamma, if gamma is one of my contexts there in the index category, is, of course, by Uneda here, it's just a map into the presheaf of types. So that's the interpretation of this judgment. A is a type in context gamma. The interpretation of the judgment little a is a term of type big A in context gamma, which is one of the primitives of Martin-Duff type theory, is just a lift like this across this typing natural transformation, this presentable natural transformation. And then the context extension operation, which is an important one, it was the first of my inductive rules there that I showed you, which was how you take a dependent type and turn it into a new dependent context. That simply is the condition that this map is presentable. So when I pull back along any type, I get a new type and a substitution, and that's the type in the extended context, and that's this presentability condition. So to say that the presheaf of types and terms over the category of context and substitutions is presentable is to say that it has this context extension operation. And really, if you go through now, as I do in a paper that you can look at if you're interested in this sort of thing, you get exactly the rules for a category with families in the sense of Dupierre. So that's a neat, already starting point for our axiomatics for models of Martin-Left type theory. We have the category with families boiled down to this one condition, that we have a presheaf that is presentable in the sense that I said. Okay, so now we want to look at the type formers, the sigma and the pi, and that's where the polynomial functors start to play a role. So let me just remind you that if I have a locally Cartesian closed category, such as the category of presheaves, and I have any map in there, which I could be thinking of as one of these models of type theory, but any map at all gives rise to a polynomial endofunctor. Richard was just talking about the category of polynomials on set. Well, more generally, as most of you know, you can take a polynomial like this by pulling back to the domain, pushing forward along the map itself, P, and then forgetting the indexing. So here's a little picture of it, right? Here's my map that's giving rise to the polynomial functor. I want to make a functor at the argument x coming from C hat. I just cross with the domain, push forward along P, that gives me this map, and then forget the indexing. So that's the polynomial P applied to the object x in this diagram. And here's the expression of it in the more familiar polynomial notation there. That's why we call it a polynomial, because it looks like one. Okay, so there's a polynomial functor. Now, we're going to need to know what the universal property is of such a polynomial, and many of you already know that. If I have a polynomial functor, I apply it to an argument x, and I map into it from some arbitrary object, then maps in correspond to pairs, the first factor of which is a map into the base of the, well, maybe we call this the signature of the polynomial. It's the thing that gave rise to the polynomial functor. And then you pull back the fiber, and it's a map out of the fiber into the argument that you've applied the polynomial functor to. So that's a good universal property for polynomial functors. And let's take this one now and apply it to its own base, and therefore we get a new instance of this universal property with u here in place of x, because we've applied it to u. And if we think of this now as our model of type theory, a map into the base, of course, is classifying types in context gamma. That's what we said before. And now a map out of the fiber, well, the fiber was the extended context, right? That's what I told you a minute ago. And now we have a new type because it's valued in u. So pairs like this are nothing but types in extended context, right? So the polynomial functor applied to u classifies, so u itself classifies types in context. The polynomial functor applied to u classifies types in an extended context. So that's the important fact that I'm going to make use of. So let's look at the pi type construction. There was that whole page of rules, remember, that I gave you before. And if we make use of our interpretation now, it turns out that those rules for the pi types are captured exactly by this one pullback diagram. I take my polynomial here, P, I make the functor and apply it to this map. There it is. And now I say, if I have a pullback square like this, I haven't specified what these maps are, just any maps making a pullback square, that is precisely equivalent to that page full of rules that I gave you for the pi types. It says that as a model of type theory, this category with families has pi types. And I don't have time to go through it all, but I can give you just a hint of why that's the case. So let's look at what's classified by a diagram like this. This thing, remember, classified types in context. Yeah? So an operation like this takes a type in context to a type, because this classifies types. Okay, so that's the pi. It takes a type in context to the pi type. If I go back to that page of rules, there are going to be all these rules, right? And this is going to be one of them. If you have a type in context, you get a pi type. Then one of the rules was the so-called introduction rule, which says if you have a term in context, then you get a corresponding term. And that's this lambda abstraction that you maybe know from the lambda calculus. And now the commutativity of the diagram tells me that this term has this type. Right? So there's the introduction rule. And now if you go through the pullback condition, what you'll see is the elimination rule says that this thing is a weak pullback, and the computation rules of type theory say exactly that it's a pullback. So that's pretty slick. We have the rule for the pi type saying something about the polynomial functor generated by this category with families. What about the sigma type? That was another page full of rules that I gave you. Well, it says the following. Let me remind you that every polynomial corresponds to an endofunctor, and if you take the composite of two such endofunctors, that's again polynomial. And so it's given by a map using that formula that I showed you. And so in particular, the polynomial p, if I square it, is the polynomial endofunctor of some map, which I'm calling p, little p dot little p. Little p dot little p is the map which satisfies this property. It represents the composite of these two polynomial endofunctors. Take that map and put it, that little p, and put it right there. And if you have a pullback square like this, then you might as well call these two maps sigma and pairing, because those are the sigma and pairing operations for the type theory. So again, presentable natural transformation regarded as a category with families will have the rules for sigma type formation, just in case this square that I build out of the polynomial has a pullback structure like that. Okay, so that's my second proposition. Here's something new that's not in my paper from a few years ago. So the identity types, that's of course an important feature in the Martin-Löf type theory. This much is in my paper, namely the identity type former is given by a square like this, where this is just the diagonal of this map. So here's the identity type formation. If I have a pair of terms of the same type, then I can make a new type. That's what this is. And there's an introduction rule here that's given by the top map. And if you make a pullback square here, which is the most obvious thing to do, what you get is the rules for Martin-Löf's extensional type theory, which is something of interest. It's modeled in locally Cartesian closed categories. But of course, for Hott, we're interested in a different version of the identity type. And now, here's how you can model the identity types. I'm going to do this very briefly. You make a pullback here, but now this is no longer a ISO here. Instead, there's a map here, and that gives rise to a comparison between the original thing and this one, and then you apply a polynomial argument here, and you get a comparison square, and a pullback structure for this comparison square is the elimination rule for Martin-Löf's identity types in the intentional form that we use in homotopy type theory. So this is a really nice argument. I'm going to have the slides online, and if you're interested in this subject, I suggest you go through it. I'm not going to go through it for you right now, but Richard Garner is the one who pointed out this very nice description of the model of intentional identity types using this polynomial machinery. So here it is. If you have such a model of the Martin-Löf type theory given by a presentable natural transformation, it will support the intentional identity types of Martin-Löf type theory. Just in case you have a commutative square like this, which has a weak pullback structure in the sense that I just sketched, and it will then model the standard Martin-Löf rules for identity types, which Per Martin-Löf wrote down in the 1980s and which have been quite mysterious for many years. So that's how you describe that structure. Now, here's the place where there's a missing slide. I could have added a slide where I told you about weak models of type theory Andre Joyal has given a very nice description of such models using what he calls pi tribes. So if you're familiar with this literature, there's a thing out there called a pi tribe. An example, he's abstracting from examples of Martin-Löf type theory in weak factorization systems with certain additional structure, for example, Pullen model categories, which give rise to homotopical models of the intentional type theory. That's kind of the main thrust of the homotopy type theory program. And one issue there is the coherence issue that affected or infected Seeley's interpretation that I told you about way back when. And so it's a challenge to strictify such models. And that's what this theorem is telling you about, is a strictification of such a homotopical model of type theory. And this is a theorem that's due to a few people. And it says if you start with a pi tribe in the sense of Joyal, so a display map category maybe in the sense of Paul Taylor, equipped with a weak factorization system and some right adjoints to pullback for fibrations along fibrations. There, that's a brief summary. Then what you can do is you can take the presheaves on the category of contexts and take the coproduct of all of the fibrations, and that will give you such a presentable natural transformation, which moreover has that structure that I just told you about, the polynomial operations for sigma and pi, and the intentional identity types. That's quite a nice theorem. This was originally proven by Peter Lumsdain and Michael Warren, two students of mine, in a somewhat different form, not involving these polynomial models. But the idea is that this is a splitting of the codomain fibration to make it a presheaf. You take the codomain fibration, or if it's a pi tribe, you take the fibration of all right maps in the pi tribe, and then you split that. There are different ways to do this. This is the left adjoint splitting, and that will satisfy these operations. And a nice example of this, of course, is a Pullen model structure, which is our kind of standard way of modeling hot nowadays, is with a certain Pullen model structure. And last year in Louvain-la-Neuve, I told you about such a model using cubical sets, which is a Pullen model category, which is a model of hot. And this tells you that you can strictify such a model and get a very tight model of the semantics which satisfies all of the equations that the type theorist wants. It's a category with families then, with sigma, pi, and identity types. Okay, so that's that story. And now what I would like to do is try to axiomatize this kind of a model so that we can start working with them rather than just admiring them. So here's the structure that I'm looking at. Oh, I'm missing one thing, is this easy unit type from type theory. That's modeled by a pullback diagram like this, with just one here on the left, and here's my model of type theory, which I'm calling a natural model. And if I have a pullback square like this, then it's going to be a model of these unit types. So let's add that to our structure that we're interested in. And now I'm going to try to abstract this structure a little bit. So I have the pullback square that I just told you about, the pullback square here that had to do with the composition of the polynomial with itself. That's the sigma type and the unit type. Now, of course, when you have polynomial functors determined by a map, these squares determine Cartesian natural transformations between the corresponding polynomial functors. Are you telling me you agree, or are you telling me I should hurry up?
1 minute.
Okay, well, I'll see what I can do. So I have these two natural transformations, and these should look familiar to you now. This, of course, represents the identity polynomial. So I have two natural transformations like this, and you're going to wonder, that looks like the structure of a monad. And you're going to wonder, is it indeed a monad? Well, we have the type theory already gives us this structure. And the laws for the monad, it turns out, correspond to some kind of familiar, maybe, isomorphisms in the type theory, which hold up to isomorphism, but not up to equality. And the law for the pi types that I showed you before is also an algebraic structure. It's an algebra for the monad, and its equations also hold up to some familiar isomorphisms in the type theory. So we're very close here to having a monad and an algebra for the monad. I'm going to use that to axiomatize these models of Martin-Liff type theory that I've been slowly approximating. So I'm going to say a Martin-Liff algebra in a locally Cartesian closed category is, well, a tiny map. That was the context extension condition, remember? So in any LCC, I can say that a map is tiny. And then I equip it with these three pullback squares, which are simply determined by this map. And the conditions make sense now. And that's a Martin-Liff algebra. And by that strictification theorem that I just told you about, we know that whenever you have a right proper model category, then there's a Martin-Liff algebra in there. Moreover, the pi tribe condition told us that that Martin-Liff algebra has identity types. So if it happens that this map is univalent, as was the case with the example that I gave you last year in the cubical sets, then the monad and algebra structures on that associated monad structure will actually be satisfied up to identity in the sense of the identity types. So that's a very neat characterization of these models of Martin-Liff type theory, is that you have a monad and an algebra for the monad in this setting. And so now we're off to the races, as it were. We can start looking at morphisms of these algebras and consider what the free algebras are and so forth. So that's the whole story that I wanted to tell you about, and the slides I hope will be available. If you're interested in this subject, let me know. I'd be glad to discuss it further with you. Thanks.
Okay, thanks, Steve.
Sure.
Questions?
My pleasure.
Oh, sorry, yeah.
Firstly, thanks for the talk. I find the note that you ended on as kind of univalence as strictifiability, that's quite compelling. Was this known already, or is this a new kind of perspective?
No, this is new stuff. I mean, except for where there's some reference to some past stuff. Yeah.
That's really cool. Thanks.
Glad you like it. I think I went kind of fast there.
Morgan.
Oh, yeah.
In the motivation section, you said, when we first talked about finding objects, you said that pullbacks are creating some coherence conditions. And I'm sure this was formally answered by the end of the talk, but pullbacks did show up a lot throughout. So how do those coherence conditions get avoided by the end?
Yeah, that's a good question. So this is, maybe I should have said, what we're doing here is a kind of generalization, if you will, of the internal logic of a topos. In a topos, there are two ways to model the logic. The logic lives in the subobject vibration, right, over the topos. But you can also model it by homing into the subobject classifier, right? And there are some operations on the subobject classifier, the meet and the join, and the quantifiers too. And then the coherence, the substitution laws you get for free because you're homing into something on the right. Like the Beck-Chevrolet conditions. You get them for free because you're homing in for the quantifier on the right. And then the Beck-Chevrolet is just precomposition being associative. And here too, we've constructed this gadget, this Martin-Liff algebra, and now all of the coherence goes away, or the problems go away because you're just homing in, right? So instead of pulling back some maps over the different contexts, you just hom in from the context into this one structure. So it's kind of like a hiding algebra, but a kind of proof-relevant or hiding algebra living inside the topos of free sheets, and homming in is what gives you the type theory without any coherence problems, or even the Beck-Chevrolet conditions arise for free then.
Okay. So, I'm sorry, we better leave the further questions for the break. So let's thank Steve again, but don't go away just yet, please.
Okay.